Bueno, buenos días a todos, gracias por acompañarnos. Bueno, este es el primer desafío que hacemos del proyecto 058 compartiendo con ustedes. Quería comentarles que, bueno, yo soy la coordinadora interina de este proyecto de INTA, pero hay muchos colegas que estamos trabajando en Argentina en el tema de gases de efecto invernadero. Y habíamos conversado sobre la posibilidad de hacer un ciclo de capacitación para especialistas que sea continuo en el tiempo. Bueno, y hoy nos encuentra acá con esta idea, que les voy a compartir en la pantalla. Un segundo, por favor. Este ciclo que se llama de webinars que se llaman Sumando ConCiencia GEI. Hoy empezamos con nuestra primera expositora. Sebastián después les va a contestar por qué. Claudia Wagner-Riddle. Thank you, Claudia, for stay here right now and for the future presentation. Nosotros pensamos en un ciclo de conferencias generado en el marco del proyecto y con interacciones existentes. Hoy en día en Argentina hay un montón de gente que están trabajando en el tema, pero también tenemos relaciones e interrelaciones con colegas de todo el mundo, con redes, particularmente hay representantes hoy de la red latinoamericana de huella de carbono, con redes en colegas en Perú, en Chile, en Ecuador, en Nueva Zelanda, en distintos lugares. Entonces nos pareció que era interesante generar un espacio de encuentro entre especialistas para escuchar, conversar, compartir, planear, exponer y por qué no hacer interacciones o futuras propuestas sobre la temática. Hoy por hoy encontramos a Claudia Wagner-Riddle, que fue la directora de Sebastián Cambareri, que es el otro copresentador de esta jornada, y quería darle la posibilidad a Sebastián, que va a ser aparte nuestro traductor oficial, que por favor presente a Claudia y cuente sus interacciones. Por otro lado, quería contarles cómo es la organización de la presentación. Claudia va a tener 40 minutos para la presentación, 20 minutos para preguntas, y estimamos la finalización del evento hora argentina entre 12:05 y 12:10. Durante la presentación les pedimos por favor que apaguen sus cámaras y micrófonos. Este evento también se está grabando en YouTube. Así que esta presentación después podrá, Claudia accedió que fuera colgada como para que todos la compartiéramos posteriormente si tenemos problemas de conectividad o nos gustaría repasar algunos de los conceptos. No sé si me presenté, mi nombre es Claudia Faberín también, otra Claudia dentro de la sala. Y bueno, le pedimos a Sebastián por favor que comience con la presentación de Claudia. Muchas gracias. Ya dejo de compartir. Sebastián, por favor.
Sí, perdón, estaba el micrófono apagado. Gracias, Claudia. Voy a presentar quién es Claudia Wagner-Riddle, que fue mi advisor en la Universidad de Guelph, donde obtuve mi doctorado en Ciencias Ambientales. Claudia es profesora de agrometeorología en la School of Environmental Science de la Universidad de Guelph, en Canadá. Ella es originaria de Brasil, pero realizó su formación básica en la Universidad de Sao Paulo y sus estudios de máster y doctorado en la Universidad de Guelph. Es experta en aplicación de técnicas micrometeorológicas para medir emisiones de gases de efecto invernadero desde la agricultura, y su investigación apunta a una mejor comprensión de los procesos que llevan a la emisión de GEI y a la identificación de prácticas de manejo que reduzcan las emisiones y el impacto ambiental de la agricultura. Claudia es miembro de la Soil Society of America la American Meteorological Society y la Canadian Society of Agricultural and Forest Meteorology. Además es editora en jefe de la Agricultural and Forest Meteorology y fue recientemente designada directora del North American Regional Chapter de la International Nitrogen Initiative. Y fue premiada en 2020, en este año, con el premio Norman Bourlag de Excellence in Crop Nutrition. Claudia Wagner-Riddle ha publicado más de 150 papers y tiene un H-index de 40 en Google Scholar. So, okay, that said, that is the whole presentation in introduction in Spanish. Now I would be long and I leave it to you, Claudia.
Thank you, Claudia.
Thank you very much. So everyone can hear me okay, I hope? The sound is good?
Okay,
okay. I'll get started right away. So thank you very much for the introduction and for having me today. I'm going to structure my presentation. I'm going to give you a little bit of background, but I'm sure most of you are very familiar with some of these numbers, and then move into the structure of the talk. So starting off with the fact that greenhouse gas emissions from agriculture are estimated by FAO to be around a quarter or 24% of overall emissions. Now I should point out that of these 24%, half are due to land use change, and half are attributed to the category of agriculture that includes what I'm going to be showing next. So these are emissions. So overall, the agriculture part for the world is around 5 gigatons of CO2 equivalent. Again, that doesn't include the land use change. And it's distributed according to the world region as shown here. If we break up each one of those in terms of the sources, we see here, a number of a good proportion of the emissions due to animal agriculture, and then crop agriculture, of which again part of this is used to feed animals. And then depending on the region, we have the predominance of either enteric fermentation. Well, actually enteric fermentation kind of predominates everywhere, but we may have soil emissions a bit larger, such as here with stored manure and crop residue and so on. So these sources then are shown here in a bit more detail, with the fact that we get methane from enteric fermentation and manure management, and nitrous oxide from manure management, soils, and we can have some obviously CO2 exchange and some net CO2 uptake potentially in agriculture as well. So I'm going to concentrate my talk on nitrous oxide and some CO2, but I do show here some data that we've collected before from these large manure tanks. In this case, it's a dairy farm where they also had later installed an anaerobic digester. And here the data is shown over the course of 1 year from January to December. And once the conditions are warmer for our region of the world, that's when we get large emissions. In terms of nitrous oxide, as I said, I will expand a bit on that. But when we apply fertilizer, as shown here in the 4 arrows, we get peaks in emissions over time. So the main point of this slide is to emphasize that fluxes are highly variable in time and space. If we go into a bit more like nitrous oxide, recently there was a new global and low budget released publication in Nature that really emphasized the fact that the agricultural sector is the main source of nitrous oxide, and that we are in a trajectory of the worst case scenario, shown here, like different projections depending on economic growth and mitigation practices. And the line in yellow and purple, as well as the average of those two, is the current situation. So we're in this high constant or emission trajectory, and we need to revert that. So for my talk today, what I want to focus on is getting a little bit more into what drives these, the nitrous oxide and CO2 emissions, how we can best measure fluxes to capture emission events, and as well evaluate mitigation practices, and then how we can manage agroecosystems to mitigate agriculture's impact. So I'll show a few examples of results that we have. So starting off, again, a focus on nitrous oxide, because that's what our group has worked with the most. When we add nitrogen in any form, be it synthetic fertilizer, in animal manure, or as legumes or crop residues, they enter the nitrogen cycle in the soil and result in either ammonium or nitrate concentrations increasing. And the first part of the diagram shows nitrification, and then the second part, or to the right, denitrification. So this is based on Firestone and Davidson, who proposed this so-called hole in the pipe model, with the idea that the rates of nitrification or denitrification are the flow within the pipe, and the N2O emission is, or the byproduct of N2O is, escapes through this hole in the pipe. And there are different factors that control the size of the hole, as well as the nitrification rate. In general, for N2O emission, the largest amounts come from denitrification. So when we have high water content resulting in low oxygen, or even a carbon source that will consume oxygen and decomposition, and also result in anaerobic conditions. So the N2O emissions have been described as occurring due to hot spots and hot moments. And what that means is we have a lot of spatial variability. So some areas that emit a lot of N2O and others that emit less. And we have times when we get a lot of N2O and times when we have less N2O. So we've described this in a recent paper. And basically we've describing it as, depending on the spatial scale, we will have hotspots or hot moments triggered by different effects, but they're all related. So at the microsite level, you know, reduced oxygen due to decomposition, or an increase in carbon, or an increase in these ammonium and nitrate level, will result to N2O. At the field scale, this is associated with addition of farmyard manure, so basically solid or liquid manure, urine, inorganic and crop residues. And then the timing is induced by either rainfall or irrigation, in cold climates by thawing or frozen soil. And then as we go to the landscape scale, we have areas where with lower drainage class, or where organic matter or nitrogen have accumulated, that may lead to high N2O. And then regional or global, we have areas where animals are concentrated, or where nitrogen is overused, that can lead to high emissions. In terms of temporal, or these hot moments, I'm showing two fields that were side by side, so same soil and weather conditions, but very different timing in emissions. So I'm asking here, you know, what is driving this difference in when the N2O emissions occur? And I'll be answering that question in the next 2 slides. So first, for field 1, you can see the arrow here. And what that was nitrogen addition at planting, fall in the form of urea, broadcast and then incorporated, followed by rain, 3 rains that increased the water content, so it induced air anaerobic conditions and then resulted in these N2O peaks. The field 2 had urea ammonium nitrate applied at the corn 6 leaf stage, so not at planting, but 40 days after planting, where it was injected into the soil. And we then did have rains as well. So we had this hot moment occurring at a different time. So it's clear that we have to have a combination of factors, high nitrogen levels, potentially carbon levels, plus that high soil water content induced either by irrigation or rain that will result in those N2O emission events. In terms of carbon, just a reminder here, so we're interested in knowing if these agroecosystems are sinks or sources of carbon, and it's quite dynamic, the carbon fluxes, where we first have uptake through photosynthesis with resulting in gross primary production. And then we also have ecosystem respiration, either soil or plant. And we can't forget that we remove carbon from the soil at harvest, that, you know, unless some of that carbon is returned in the form of manure, that is a loss for the system. So we're really interested in the net ecosystem carbon budget, which is the difference between the gains and losses. So these fluxes are also very dynamic and involve both carbon uptake and losses. So this brings me then to the second question that I would like to talk to you about today, which is how can we best measure these fluxes so that we can capture the events and also at the same time then evaluate mitigation practices. So I'm going to start with chamber methods, which involve basically covering the soil and capturing the increase in concentration over time through manual sampling of the headspace of air within that closed volume. The picture down here on the left is from Sebastian's PhD research, where we made it to the Soil Science Society of America journal cover, showing a number of chambers being deployed in an experiment. Chambers can also be automatic. So this is my PhD student who's just about to defend. So this is an automatic Lycor chamber interfaced with a Fourier transfer infrared analyzer that is able to measure CO2, N2O, methane, even ammonia. So this works well for soil chambers, but if we want to also determine what's happening in plants, you have to go a little bit extreme, such as in this case, it's a picture I took once when I was visiting Sweden, where they had this free air or enrichment of CO2 atmosphere with these huge chambers, a multi-million-dollar project. So that's often not that feasible to do, and I'm just showing this as an interest. So in terms of chambers' advantages and disadvantages, low cost and simplicity, particularly for the manual chambers, they are labor intensive, not can be, as you've seen from the previous picture, it involves manual sampling. They can be left in place only for a limited amount of time because they alter the microclimate, except for automatic chambers, which automatically open and close, so avoiding that change in microclimate, although there are still some effects in terms of rain capture and so on. So for long-term studies, it's a little bit, they're not ideal. And also they only capture emissions from a small area. And that's particularly troublesome because of what we talked about, having hotspots within a landscape. So you really need to use a large number of chambers to try to characterize a large area. But they're very good for situations where we're comparing several management practices at a small plot, like agronomic type experiments. And basically they're used, like I would say 99% of everything that we know about N2O is from these types of studies. Now, micrometeorological methods do have advantages as well. And they work by basically, if you think about a large invisible chamber placed over an area that is quite level and homogeneous, where we don't have anything happening in the horizontal. So basically any advection of gases is zero. So what's going in and coming out is the same. And if we set up instrumentation above the surface, we're able to capture the N2O leaving or going in, but that's very, very rare that we have consumption. And then the CO2 flux in both directions. So these areas have to be homogeneous level and relatively large, so larger than 10 hectares. And you measure at this point, you're measuring the soil flux of N2O, unless there's some reason to believe that plants are sources of N2O, but that's not really been shown widely. And then, as I said, you measure the net ecosystem exchange of CO2. And just reminding us what that is the net between photosynthesis and all these other respiration values. So the instrumentation is set up above the vegetated surface, and that is because we have limitations as to what we can measure within the canopy and the theory that can be applied to derive the flux. But we're very good at what is happening above the surface. This diagram shows these eddies of different sizes, large and small, which are these twirls of air that are transporting gases either away or towards the surface, depending on where the source is. So for N2O, if we have a source here, and as this N2O diffuses out of the soil, it gets picked up by this turbulent motion and is moved upwards and passes the sensor. Now I will show you a little bit more of that. This is a birthday cake that one of my students did based on this figure, and just a picture of when Sebastian was part of my group some years ago. And cake and beer is always the best thing to have. So if we measure at some height in this layer close to the ground, in the turbulent surface layer, the flux is very close to constant with height for non-reactive molecules. So what that means is that I can measure here or here or here. So there's a kind of sweet spot, as we say, where you don't want to get too close to the canopy because that will impact the fluxes. But as you move away, what happens is, if we think of that the footprint gets larger. So if you're relatively close to the surface, you're capturing what is coming from a distance upwind. And if you move up you get a larger footprint. And if you move further up, you get a larger footprint. So we want to make sure this footprint is within the area that we want to measure, and it's not measuring, the neighboring field. We use a ratio of about 100 to 1 in terms of this height to fetch. So we want 100 meters for every 1 meter that we go up, or so, somewhere between 50 to 1 or 100 to 1. So this is just shown in different forms. So the instrument sees the sum of the flux from all these areas where there's a certain distance where the contribution is at a maximum, as shown here also in 2D form. So the further you move away, once you're at 1,000 meters for typical measuring heights, you're not really capturing anything that's outside of that. And the same is shown here. If you have your instrument at 1.5 meters, you're capturing 60% of the contribution, quite close, and then the rest is further away. While if you're at 4.5 meters, you're getting 60% of the contribution from a much larger area. So, and this depends on a number of things, but particularly height of measurement, what kind of surface you have, the stability conditions of the atmosphere, and so on. So in general, the advantages then are for Micromap methods are that the fluxes are integrated over large areas. You can have a high temporal resolution because we're measuring every half or over half-hour intervals. So that's ideally suited for long-term monitoring without interfering with the surface. But the disadvantage is that the sensors cost a lot, and you need trace gas analyzers that are quite portable and rugged and can be deployed in the field stable for a long period of time. And the final disadvantage is that the number of treatments that you can monitor is quite limited. So there's a trade-off. And what I find over the years, we've tried to pair what we do in the Micromap plots with chamber experiments. So looking at using chambers to get a sense of what the controlling factors are, and then using the Micromap to get the annual totals, including over the winter time, which is a big source of emissions, as you will see in a minute. So Micromap methods, the preferred and standard is called an Eddy covariance method, and it's preferred because it's a direct measurement. There's no assumption or parameterization. The flux gradient method, on the other hand, uses an empirical parameterization, but it does have the advantage that it can be used for what I call multi-plot sampling, up to 4, which is, for an agronomic experiment, this doesn't sound a lot, but for Micromap, in the Micromap world, that is, it's many simultaneous measurements and emphasizing with the same analyzer. So I'll just give you some idea of the instrumentation needed. So in the Eddy covariance system, we use a sonic anemometer to get the 3D wind speed, but particularly we're interested in the vertical wind speed because that tells us if eddies are moving up or down. And at the same time, we want to know what is the mixing ratio or mole density of this air that's either moving upwards or downwards. So we do have open path analyzers for CO2 shown here, but these are not available for N2O. So for N2O, you have to then use a closed path analyzer. So here is one setup we had in the field where we have the sonic anemometer and then tubing that's pulling air down to go through this analyzer, which normally is closed and just looks like the box on the right. But here it was open to for some calibration. So basically the rule is that we have a tower and the analyzer sits at the bottom of the tower, and that the limitation is that you don't want tubing that is too long because you lose the high frequency needed to determine the covariance between signals, as I will show you in the next slide. So for each field, you need a tower and an analyzer. And that becomes then a bit of a disadvantage for the eddy covariance method. So this is an example of 10 Hertz data. So data is being collected at a rate of 10 data points per second. Sometimes it's even goes at 20 Hertz, depending on the setup. And this is the vertical wind speed. You can see the variations, and then the variation in the N2O mixing ratio. And the question here is, can you see the covariance of the signal? And I'll let you look at this for a moment. And I don't have the chat function here looking at me, but I would expect that you could see that when eddies are moving upward, which is going to the positive wind speed, they're also carrying N2O from the soil up past the sensor. So we talk about the signals co-varying, and this is where the method gets its name from. Another one here where upward moving areas, eddies are carrying that high N2O from the soil up into the atmosphere. So if we didn't have an emission event, the N2O would basically be flat, and you wouldn't get any positive covariance between the signals. So the analyzer requirements, as you can see, is that they have to respond fairly quickly. They have to have a high frequency cutoff, like and not like 6.3 Hertz, for example, not 2 Hertz, because then you lose a lot of the high frequency signal, and low instrument noise on the order to 1 to 2 parts per billion on volume. Now, going back to N2O and the dynamics of it, what we're interested in are looking at management, but we also have superimposed the variable soil conditions driven by weather. So that interaction of weather and management. So for mitigation studies, we really want side-by-side plots, because otherwise, if you do the measurement in 1 year and then in the next year you do the change in management, well, if the weather is different, that doesn't tell us anything. So to compare 2 or more practices using an eddy covariance would require more than one analyzer, as I was just saying. So the alternative method that does not rely on the covariance of the wind speed and N2O is the flux gradient method. So it's basically an integration of flux with height. And this is the equation we use in an aerodynamic approach of the flux gradient method. And the main thing that we're measuring is the difference in concentration, either N2O or CO2, between 2 heights measured using one trace gas analyzer. And then we still use the sonic anemometer, but to get sensible heat and friction velocity, just two parameters that we can measure directly with the sonic. With those two, we can calculate these stability parameters, which is the parameterization part of the equation. And then Z2 and Z1 are just the heights, and D is a displacement height, which is an offset due to vegetation height when that is present. So the advantage of this method then is that we can set up more plots, and what I call the 4 for 1. So I don't know if you have that in Argentina for sale when you buy 2 for the price of 1. So it's basically a take on that, where we have 4 plots that are quite large. They're about 4 hectares, and they're within an aerodynamically homogeneous area with the same crop usually. And we set up these intakes in each one of the 4 plots. And in the center, we have a trailer and tubing that goes from each plot to the trailer. You can see 4 of them here, 1, 2, 3, 4. And that's all controlled by data loggers that will switch between plot 1, plot 2, plot 3, plot 4 in time. So we do half an hour for each and able to measure 12 values over 1 day per plot. The tubing, after it goes through this manifold system, goes into a tunable diode laser trace gas analyzer, which is the same analyzer I was showing in the previous setup, that is able to determine the concentration at very high frequency over time and precision. So here is an example. What we've been able to do with this type of measurement is we set it up and we basically run it 24/7, 365 days of the year. And a lot of our work has been done because we are in a cold climate here in Canada, where the soil does freeze seasonally. And here's an example from January to January, February, March, April, with air temperatures. You know, we're in a warm part of Canada, so it doesn't get that cold, but we do get periods of -10, -20 sometimes, and a little bit of snow. So we had, the red line is the flux, and we see that every time it thaws a bit, we get these peaks. And then when we have the main thaw, we get a sustained period of emissions. And we've demonstrated how important that is for the global budget. By the way, the Nature paper that I talked about at the start acknowledges that they should also look at the seasonally frozen soil, but they weren't able to do that for that study. So what we get sometimes is 1.5 kilograms of N lost over this period, which was 64% of the annual emissions. The main event, which was over 20 days, was about half of that. Okay. So I didn't talk too much about our work on freeze-thaw because I don't think it's that applicable for large areas of Argentina. So this brings me to the sort of third part of the talk, which is giving you a few examples of how our work has shown that emissions can be mitigated through practices. So starting off with, we work a lot with corn, and that's because N2O emissions from soil make up more than half of the carbon footprint of corn grain. And if we take the production, the energy used in synthetic fertilizer or fossil fuel used in synthetic fertilizer production, that brings us almost to 3/4 of all emissions associated with corn and what we call from field to farm gate. So it doesn't include consumption, but just the production of corn, where SFN is the synthetic fertilizer nitrogen. So it's really important for our region to find ways to decrease this component of the emissions. So we have worked with the fertilizer industry in Canada. They have proposed this 4R nutrient stewardship program, and they are very heavily investing in training of what are called certified crop advisors. So these are basically the agronomists that make fertilizer recommendations, to use this concept of the right source, the right rate, the right time, and the right place of application. So some recent work that we have done, I will expand a bit, because of course this is a good framework, but we still have to determine what is the right source, what is the right rate, so we can make the recommendations to farmers. So the work that we've looked at was, if we consider the curve of nitrogen crop uptake, that it really expands when corn is just past the 6th or 7th, 8th leaf stage, where it accelerates that uptake, so that instead of applying nitrogen at planting, applying it at, say, the 6th leaf stage could reduce losses. That's a question. So that would be sort of the right time. The other option would be to apply what is called a EEF, an enhanced efficiency fertilizer, which is a fertilizer formulated with some kind of inhibitor. And what we looked at was a nitrification and urease inhibitor. So the idea, we looked at two questions. If you apply it at planting, is that equivalent to applying a little bit later to reduce the loss? Because a lot of farmers prefer to apply all the nitrogen at the start or at planting, as opposed to delaying and then not being able to apply it later on. So our experiment looked at urea in both types, a regular versus an enhanced efficiency fertilizer. And so that would fall under potentially the right source. So that comparison versus a lot of fertilizer is applied also in liquid form, injected into the soil as urea ammonium nitrate, and adding a right source to that. So that type of comparison, as well as you can either apply, or looking at applying an enhanced fertilizer at planting versus delaying and applying regular fertilizer, where you don't have to pay for the slightly higher cost of the enhanced fertilizer. So here are results. I'm only showing 80 days after planting, but that's when the bulk of the emissions related to the fertilizer occurred. But we also did this analysis over the whole year, and the results are similar. So here I have a comparison of urea with and without the inhibitor, UAN with and without, and then that comparison of enhanced fertilizer at planting versus applying later. And overall, over 3 years, we find that out of the 3 years, 2 result in significant reductions, shown here and here for UAN, and here for urea. Timing had no effect, and this did not result in any difference, which is shown here. I just want to say a little bit more about the timing. I have already had shown the data here. Basically, the timing of application shifted the peaks, but had no reduction. And it's a little the luck of the draw, as we say, because if it hadn't rained, probably we would have had an impact. But if it does rain, then it doesn't make a difference. Now, it does give you the opportunity to adjust rate when applied in season. And I think this is where the timing can really have an impact, but we have not studied that yet. in terms of another example is the use of perennial crops compared to annuals. So we have a big push here for increasing soil health, and perennials are really important to have that in a rotation to for carbon input and just general soil health benefits. And what we see, again, this is an example for freeze-thaw emissions, but we saw a 60% reduction in emissions in the hay field compared to corn, even when adjusted for the nitrogen application. So I'm getting to the end of my results. I just wanted to give you an example of the data for CO2. The net ecosystem exchange can be partitioned into respiration and GPP through basically kind of a modeling approach and separating out nighttime and daytime data. And what you see here is the convention that we use is that positive is flux away from the surface, negative is flux uptake, so that anything on this side is source, and anything on this side, the negative, is a sink of CO2. So we see that compared to corn, hay has a longer season. Corn is planted here and harvested here. It doesn't take up as much, the hay, as the corn, but it takes it up for a longer period. And also the respiration is less. These two arrows show when the hay was cut. But overall, we would like to know which one is bringing in more carbon, which is basically the difference between this loss and this gain. And also considering harvest. So that's what's shown here. Don't worry, or let's forget about this difference, because there wasn't really any in terms of manure treatment, but the red is hay and blue is corn. So this is the net GPP. The carbon added in the form of manure was quite small. The carbon removed, though, is larger. And then this is the respiration loss. So the difference between these two gains and these two losses is what we're left with here. And it basically shows that the hay field was, over the 3 years of study, was neutral, but the corn actually had a net removal of carbon. So, you know, this then can be considered in things like, you know, what do we feed the animals and dairy cows, for example, and would that result in a reduction of the carbon footprint of milk? So I'm going to finish up with a slightly different take. We've worked with an agriculture economist to try to answer the question, are farms that are more profitable, do they also have a lower carbon footprint of milk? Is there a trade-off, or is it a win-win situation? Now, I should note that we didn't consider any mitigation practices in this. So this was basically a study that used data from 200 farms and did the analysis. So it's basically our status quo in Ontario. And what we found is this bell curve in terms of profit per cow per year, and the carbon footprint, which I'm not showing here, was inversely correlated. So basically, we had that the 25% of farms with the lowest profit had the highest carbon footprint. So those were the worst farms in terms of greenhouse gas emissions. The ones with the highest profit were the best in terms of carbon footprint. And that had to do with more profitable farms use less feed, less fuel, and a whole bunch of other inputs because they're basically more efficient, and they basically produce more milk with less. And then the question is, how do we move producers that are at this lower end to the higher end, right? And is that through investment in facilities, in education? So that's, I'll just leave you with that question. So overall, here are some concluding remarks. I talked to you about the advantages of eddy covariance and flux gradient, how they can capture the temporal variability and integrate fluxes over a large area, and that this multi-plot flux gradient method that we have developed is ideally suited for N2O emissions. We have done a lot of work in spring thaw that I talked to you about. And then we've also evaluated several mitigation practices. The ones that have been shown to reduce, some of them I have not shown here, but rate adjustment, use of inhibitors, this is for N2O, perennialization is using cover crops. Again, I didn't talk about this specifically. And I think we're really moving towards combining a number of practices so that we can bundle these practices into packages that also consider costs and recommend those to farmers. So I'm going to stop here, and I guess we have some time for questions. Thank you for your attention.
Thanks, Claudia. Very wonderful presentation. We have a couple of questions that were dropped in the chat.
Yeah.
I will
maybe I'll stop sharing. Or...
perdón, Sebastián, yo te fui copiando las preguntas en el Drive.
Sí, sí, las estoy viendo.
Ok.
We have one question about methodology.
Mm-hmm.
This is the Micromap method,
Yes.
about the ratio 100 to 1 that you mentioned.
Mm-hmm.
The question is if these 100 meters are taken in the wind direction for each meter of height.
Right. So it's you basically have to do the analysis on a half an hour by half an hour basis. So if the equipment is set up in the center of the plot, then you look in all directions and you try to meet that. So 100 to 1 is what you will see in micrometeorological texts and so on. It varies a lot with wind speed and stability conditions. So we usually use a 50 to 1. So we relax that criteria a bit because that captures up to like 85 to 90% of the flux. And sometimes you can set up, if you don't have enough fetch, you can set up your tower in the direction so that you have that maximum fetch in the direction of the prevailing winds. So some wind directions, you then throw the data out and you keep the one where you have the best fetch, if that makes sense.
Good. Good. We have another question here. It's from Nuria. She is asking if you found any difference between the fluxes that you measure with the non-steady state chamber and the eddy covariance method.
Mm-hmm. So we have done the comparison with the flux gradient method in chambers, and we have done flux gradient versus eddy covariance, but not chamber versus eddy covariance. But I can say that by difference, we can say like flux gradient and eddy covariance, we had fairly good agreement. The one problem is that the eddy covariance, you can't, if it's raining or if you have any kind of droplets in the air, the sonic anemometer doesn't give good data. So it has happened before where we completely missed an emission event with eddy covariance, but we were able to capture it with flux gradient. Now, going to your question in comparison to chambers, we've done some comparison, and you know, it's not bad. The problem always with that type of comparison is that you're actually not measuring the same thing in a way, because if you think of the chamber as this type of footprint that is quite small, and the whole field that you measure with the eddy covariance, there's a lot of variability. So to be a fair comparison, so to speak, you would have to have like hundreds of chambers in that field, and you would have to have them within the footprint depending on that wind direction. So people have tried to do that in the past, and they basically end up like, oh yeah, comparison is okay, but a lot of uncertainty or variability.
Okay, there is another question here. It's related also to the eddy covariance methodology. They are asking if the brand of the equipment is Campbell, and you have to maintain continuously the laser with liquid nitrogen.
Yeah, so the equipment that we've used for nitrous oxide emissions has been Campbell Scientific. The main reason, or there are a couple of main reasons for that. Number one was that this equipment was actually developed here at Guelph by Professor Thurtell, and then patented and sold by Campbell Scientific. So I actually started using the equipment back in my postdoc years, when we were using still the prototype that had been originally built in Guelph. So I'm very familiar with the equipment and so on. The second reason, so since then we have obviously bought a few new ones from Campbell, and we usually go that route because it's cheaper than the alternatives in the like the Aerodyne and Picaro, and those, I mean, we're still talking about 100,000 US dollars versus 200. You know, it's still expensive. So that's what, yes, it's Campbell, and it is the older models are liquid nitrogen. So we're still running some models that we've run for more than 10 years with liquid nitrogen, but the new ones are not. They are ambient temperature lasers. So I haven't had any other experience with eddy covariance N2O, but for CO2, we use the open path LICOR. We've also used some closed path Campbell system.
Okay. We have another question, but it's related with drivers. Andrea Enriquez, she's asking if the emissions of N2O associated at snow events are also related with the massive melting, or some temperature factor, or some combination of both.
Yeah.
And she's also asking at which temperature you have the maximum emission of N2O.
Yeah, so it seems to be a very different driver. So in non-frozen soil, the general concept is that higher temperature, as long as you have water, the anaerobic conditions, you get more N2O. For freeze thaw, what we see is it's very much the presence of liquid water that starts inducing emissions. So the thawing process is a process where you first like get a lot of energy into latent heat of fusion for melting, and none goes into, or energy only goes into warming once it's all melted. But we see those big emissions right at the start when we get a little bit of temperature above zero, air temperature, and we have a melting of the first few millimeters, we get big emissions. So we have looked at temperature, and we've seen that there is a response that tends to be up to 5 degrees. We get this kind of higher and higher emissions, but then past 5, I guess the soil starts drying out enough so that it's not anaerobic enough, or it may be also going into complete denitrification, because that seems to be one of the proposals, is that in cold conditions you have denitrification, but it's not complete. It stops at N2O, while if it warms up a little bit more, you can have complete denitrification.
Good. The next 2 following questions, they are about management. There is a question here that is, it's about, we have several corn belts, we can call it like that in Argentina, where urea is applied at planting. So the question is if an urea with an inhibitor applied by surface covering, if this, I mean, how can this could be applied to a condition in Argentina where we don't have that, you know, snow cycles or a very cold climate?
Mm-hmm. So if I understood correctly, if it has similar impact of applying the inhibitor, sorry, I didn't understand your translation, but al voleo and a la siembra, what does that mean?
Planting. So it's a planting, and it would be spread, like surface spread.
Without incorporation?
Exactly, yeah.
Yeah, so that is a problem. We haven't measured ammonia emissions, but I have a colleague who has done a lot of that work. So if it's surface applied, you know, you get ammonia volatilization, so you're getting a lot of loss that way. And actually, one issue of applying just the urease inhibitor and not the nitrification inhibitor is that you reduce that volatilization, so you're keeping more N, and then you're actually getting higher N2O, unless you adjust the rate or you apply a nitrification inhibitor. So I think ideally it would be to incorporate, but I know that that's an issue with no-till systems, right? So then the other option, of course, is going into injection, which requires equipment and all that. So I'm not sure if I completely answered, but those are my thoughts on that.
Okay. There is another question here that is about strategies. So what, according to your opinion, would be the best strategy to change, you know, the mind of the farmers, like for opt or for to choose from like having less income to more income, to improve the situation, not only in economic terms, but also environmental terms?
Mm-hmm. Yeah, we've been talking a lot about this because the question is, I mean, the practices that are really obvious, farmers are probably already doing them, right? Like it's that idea that farmers are business people, at least larger farmers, right? Like I don't know exactly the situation in Argentina, how much like small subsistence agriculture you have. I don't think it's mostly like larger operations, right? And those farmers that have machinery and all that, they already, they're for the most part business people, and they're trying to optimize their income. Although it begs the question, like even here in Ontario, very rich province, you have those farmers on the lower scale of profitability. And I'm not a social scientist, but I think it probably has to do a lot with like the age of the farmer, if they want to take a risk or not. And then it brings like, how do you get those people to do the right thing and consider both, you know, the efficiencies, but the environment. And I think in a way it's better to, instead of doing the both, can we in a way couple the two, where you say, do this because, you know, it's more efficient, and the environment is kind of a side effect of that, because the farmers are not going to, if they're losing money, they're not going to do it, right? It has to be sort of both, unless, like we've been talking a lot about bringing income in from ecosystem services, that kind of thing, but we're still quite a ways from that.
Okay. There is another question from Carlos. Carlos, do you want to open your mic and you can do the question like upload?
You're referring to me?
Yep.
Okay, thank you very much. Thank you very much, Dr. Wagner, for your excellent presentation. I really enjoyed it.
You're welcome.
My question is related to exploiting BNI, the biological nitrification inhibition, in crops, in both in perennial and in annual crops. Do you see any future in this strategy to reduce emissions of nitrous oxide? That's my question.
Yeah, so I haven't worked with that. I think that there's a lot of potential for some innovative products. I gave a talk the other day to the Canadian Fertilizer Products Forum, and I basically, my talk to them was unintended end losses. Can we do better? And then I cross it out and says, we must do better. I think it's a challenge to fertilizer industry, but also people that are working with products to try to develop and exploit more the biology of the soil. I think we've really had a sort of chemistry focus on crop nutrition. This is not my area, so I'm looking forward. I was actually asking the other day, a colleague of mine, is there any product that we could test at the larger scale? And he didn't think there was anything yet. But
no, I was thinking more in terms of plants. In tropical forages, we have plants that species that inhibit nitrification in the soil through exudates in the roots. And apparently this process could also be exploited in maize, could be exploited in other crops. So it's more a genetic approach to inhibiting the nitrification in the soil as a means to reduce emissions of nitrous oxide.
Yeah, I think that is like I know of that work. Is it with I'm trying to think of the name of the pasture.
It's Brachiaria humidicola.
Yes, yeah, very common in Brazil.
Yes.
But yeah, so I don't. Yeah, there's lots of work to do in this area, because pasture, yeah, that's fine, but how do you incorporate that into annual crops?
Yeah.
And I think yeah, I think there's lots, there should be lots of investment in this area.
Well, there is time for one last question.
Yeah.
The question is,
I have class.
yeah, I know. We know that your schedule is very tight, so that's, the question is, sorry, someone did the question in the chat here. Which one would be the expectation in terms of environmental services from stopping using urea and instead to use another biological strategy to fertilize?
What would be the expectation? Well, I think it's kind of continues with what we were just talking about. So I think using more plants and soil biology, like here, there's a lot of interest in cover crops for soil health. And actually our recent work, it's just a 1 year, we still have 2 years in the project, but if you have cover crops and you terminate them, be it oats or legumes, the N2O emissions actually go up because now you have carbon, you have nitrogen, you know, so go up once you apply the inorganic fertilizer. So how can we best combine you know, inorganic fertilizer with use of perennials or cover crops? Can we completely replace urea fertilizer? I don't quite know. You know, there's interest in doing that, but I think we still need to manage some of the inorganic, and how do you do that with all those organic sources combined?
Okay.
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 Good.
Thanks.
Thank you. Sorry, I have to run.
We know that.
We know.
We wanted to thank you.
You're welcome
for your time.
Thank you.
Yeah, and
this talk was very compelling to us, and I bet that was very compelling for all the people attending, not only for the people from Argentina, but also from the people from other countries in South America. So we are very happy for that. It was
Great.
an event with a lot of attention.
Yeah, and you have my email, so feel free to send me an email if there was a question that wasn't answered, or if you want to any other.
Thank you. Thank you. Thank you, Claudia. We are, you know, that we are busy right now. Thank you so much in behalf of all of us.
Bye. Nice
Bye.
seeing you again, Sebastian.
See
Bye.
you.
Nice to see you.
Bye.
Nice to see you.